Everyone, June 19th. Alright, let's do this. We did this yesterday, so we don't have to do this one anymore. Find the highest altitude. There is a biker going on a road trip. Road trip consists of n+1 points at different altitudes. The biker starts his trip on point 0 with altitude equal to 0. You are given an integer array, gain of length n, where gain I is the net gain in altitude between points I and I+1. Return the highest altitude of a point. Wait, hold on. On point 0 with altitude equal to 0. You're given an integer array. Oh, the gain, so goes down and goes up. And go up. Okay, so we just highest altitude of a point. Isn't just the prefix sum, right? Yeah, I think it's just the prefix sum. We find the maximum prefix sum and this shall be resolved. Yep, okay, so let's do prefix sum. We can do it tools, right? Accumulate. So we say return maximum of accumulate gain. That shall do. Okay, so accumulate has a start. I don't remember if it's a start or begin. Nope. All right. Initial. The key is initial. Okay, this one is done. I'm going to keep moving on. All right, so what do we want to do? We're going to go for, where were we? Number of the cells. No. I'm going to hit these. Row with maximum ones. Given an n by n matrix, find the 0 indexed position of the row that contains the max count of ones. The number of ones in that row and the number of ones in that row. The row with the smallest row number. Return the array containing. So this both have 1. Okay, so I guess we just do this, right? Are there any better ways to do this than just, brute force it? Count 1. Oh yeah, we have count. We do have count. We do have count. Okay. So what we can do is for each one we count. Yeah, let's just do that. Doesn't matter. What if there's no 1? Ah, it'll be 0 then. Yep. So I'll do this. Okay. For I row in enumerate mat, if res1, no, if row c equals row dot count 1, if c is larger than res1, res I and c. Now I return res. I shall do. Well, we can actually try this, right? Yep, I think this should be right. Okay, moving on. Find the maximum divisibility score. You're given 2 zero-indexed integer arrays. The divisibility score of divisors I is the number of indices j such that nums j is divisible by this. Turn the integer divisors I with the maximum divisibility score. The divisibility for every element divisors is as a score of this is 0 because no number is divisible by 5. This is 1, right? Since this is 3. Okay. I mean, how many is in the divisor? How many is in nums? 1000. So this can be brute forced. Like seriously, this can be brute forced. But we probably can do. What do you think? Wait, hold on. What if there is more than one integer, we return the minimum of them? So this is 5. Okay. Maybe the idea is to find the, I don't know, to find the factors for every number. That could be. We can find the factor of every value and then put it in. But I actually think it might be faster just to go through because it's only 1000. Just if you factor every value, that might take time. Yeah, that seriously might take time to factor every value. And then you have to combine or not to make sure that it's divisible by some stuff. Right? So might as well you just do that. Right? And then you also use a set for divisor to eliminate any of the duplicates. And for each one you just go through everything. Go through everything, and you might also counter the numbers, to get that. So my suggestion is to sort divisor, sort the unique divisor, so we go from small to large, and for each one you just find the total number of values that you can divide. Then you get this value and you say you keep the largest one. Yeah, because it's only 1000. So I think the best choice that we have is, I shouldn't say the best choice, but definitely something I will pass, So we just do that. We'll pass that, and after we pass, we can check if there's any better methods out there. Yeah, we do counter. So we say counter equals counter nums, right? And then we can say res is equal to, it doesn't really matter, res equal to what. We also need another thing, which is the ds. Okay, score. We want a maximum score, so we set to 0. And then we say for d in sorted set divisors, right? And then we say c equals for n in counter n, we should just say current ds. So for nc in counter the items, if n mod d is equal to 0, then we say c, right? And I will sum this thing. We say if current ds is larger than ds, res ds equals d and current ds. And now we return res. Counter. I didn't see that. Counter. Ooh, that is interesting. The last one. Huh. Oh, I should put this to 9 minus 1. Makes sense. Because you can have 0. Okay, so brute force works. Must work, because it's 1000. Unless it does not work. Yeah, it does. This is brute force. Because the size of nums and divisors are only 1000. OMN, right? We call it OMN. So what are the other options? I bet there are other options for this. What do you think? I mean, I don't know. What are the other options? Okay. Wait, that is the solution? Brute force? Wait, there's no other way? Brute force, brute force. This is a binary search. I just make it slightly faster. That's okay. That's okay. Move on. Minimum additions to make valid string. Given a string to which you can insert A, B, or C anywhere and at any number of times, return the minimum number of letters that must be inserted so that word becomes valid. A string is called valid if it can be formed by concatenating the string ABC several times. Holy crap. So ABC, 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 ABC. And we are given words consist of ABC only. So we have something in word, right? And we want to concatenate A, B, or C anywhere such that it makes a repeats of ABC. Very interesting question. Okay, so if we have B, yes, we're turning to ABC, right? So we need to add this and this. If I have AAA, we have 3A, so we want to turn into ABC, 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 right? So we have add BC, BC, B, so 6. If we have ABC to start with, then we don't have to add anything. So whatever it is, we're going to have some A's, right? Some B's, doesn't really matter where the B's are. Some C's, okay? So if we're given this, how would you do? Well, we count all the A's, we count all the B's, and we count all the C's, right? And this one, 1, 2, 3 A's, 1, 2, 3 B's, and 1, 2, 3 C's. But that doesn't make any sense, right? So, okay, so I think we just go C. We start with, what are you doing, man? Let's get first as B, right? If we have this, we look at the first position. Okay, that's a B. And we'll look at the next position. And it's an A, which means this cannot be any helpful. So this B has to be processed separately, right? So this B has to process separately, which means this one requires 2. Now we have an A, which is fine, right? If we find an A, we look for the next one, C. So that's bad, right? So this A need to be processed differently, and this will need 2. Oh, actually not. Because AC, it does form, right? AC, oh, hold on. So we have A, we have C. Hold on, so we might be able to, like, if it's A, because A we have AB, AC, AA, right? These are all the possibilities. If AB, definitely we try to find the next one. If AA, then we just handle this one, right? And this one require 2. If it's AB, then actually we don't know. We have to keep looking at the next one. If AC, then we just need to add 1, right? So this actually is AC. That's actually we're greedy it, right? We're greedy it. Why can we greedy it? To try as many as we can. Because if we don't do that and we do stuff, that's actually not going to be any better. So we say, okay, AC is giving us 1. Now we have A, and then we find an AC again. AC will give us 1. Now we have B. This I believe is A. So B by itself, it's, we always say we can have BA, BB, and BC, right? BA is, just B by itself. There's nothing else you can do. So BA will be 2. BB will be 2 as well. BC will actually be 1, right? And C is the same. Have CA, CB, and CC. Actually, C is the worst. C will always have to be 2. So A, we find A, oh, A, B, C. So we don't know this one will need 1, 2, 3, 4, 5, 6. In fact, it'll be interesting to see if this is right. So we have B, A, C, A, C, B, A, B, C, right? See if this analysis is right. Yes, it is 6. So I think we just check. I want to check every 2 values, right? Every 2 values. But what if it's 1? Well, if it's 1, then it definitely returns 2. Right? And then we can handle this. Now this is the question, like, what if I have something by itself, right? Something by itself, and then we can handle these two, put these two together, and then we leave something as single. Now that's what this one definitely will cost compared to, let's say, get these together, lift this as a single. What if we can get these together and leave this as a single? Or leave this as single and then put these together. Let me see. If we do the second case, okay, so what type are you thinking? We can group the second two, but we have to leave the first. But if we can also group the first two, I don't even think that's possible. Let's see. Like, the only case we can group the first two is AB, AC, and BC. That's it. That's all the possibilities we can group. All right, and if we see an ABC, definitely we want to take it. So in this case, I don't see a possibility that you can group the second two, because it's this you can group second two, but this we might as well group all of them. So yes, I do think we can just go from the start and then check every 2, right? We check every 2. And only these situations. I mean, AB is a special case. We have to check the next one. And AC and BC are special, right? They're special. All the other combinations are useless. They requires 2. And of course, if it's just a single one at the end, that shall also qualify for. So we start from this, and then we try to check the next one. So shouldn't we start by finding this? I don't know. What would be the best scenario for this? We find 2, but what if we don't have 2? Right, at the end, something gets out. Okay, at the end, something gets out, and we see okay. I have an idea, so let's try to see if this idea works. So the idea is this. I'll have I equal to 0. While I is smaller than line word. Okay. Now let's just do n equals len word res equal to 0. How about this? Okay. Then we say no if I plus 1 is smaller than n. Then we say if word I to I plus 1, well actually it's y plus 2, right? Because I want 2. If that is equal to, hold a second, we can just do I to I plus 2, right? Huh. If I to I plus 2 is equal to AB, that's a special case, right? And now we're going to say if word I plus 2, okay? So if I plus 2 is smaller than n, and this is equal to c, then I plus equal to 3. Because I plus 1, I plus 2, these can be grouped together. So we just do that. Else, which means either this gets out, it's equal to n, or this is not equal to c. Then we say res plus equal 1, okay, and I plus equal to 2. Elif word, we can say w equal to this. So we only need to do it once. Okay, so if w is equal to, elif w is equal to AB, AC, or w is equal to BC. Right, in this case, res always plus equal to 2, plus equal to 1. And I plus equal to 2. We just move on. AC, we can handle it. BC, we can handle it. We'll always move on. Else, res plus equal to 2, and I plus equal 1. Right, and then we will return res. Okay, let's give this a shot. So B will be 2, A will be 6, ABC will be 0. What else? Well, we have this, a concatenation we find ourselves, that will be 6. Well, what we need to do here is to, do a $50. I don't know. Maybe this is the case. Try another one. Or I don't know. I think the thing is this shouldn't be any confusion. Let's try. See if this one gives anything good. well, it does give us something good, so I guess that's it. So this is just greedy, right? Try to form ABC as eagerly as possible. Only 3 two-letter combinations might produce interesting result. AB, AC, and BC, right? For AB, we have to check if ABC is possible, right? Otherwise, we add 1 letter. For both AC and BC, we add 1 letter. For all other 2-letter or 1-letter combinations, we always have to add 2-letter for, we always have the 2-letter. With regard to the first letter, right? I'll call it ON. Why somebody tell me? K strictly increasing subarray. Oh, that was simple. Makes sense. Very good solution. Yes, we find the increasing. If it increases, yes, basically that's why these 3 are special, because they're increasing. So we just find all the increasing subsequence. Each increase subsequence will become, yep, very good solution. Find increasing subsequences. That's exactly the thing. Each strictly increasing subsequence corresponds to a final and eventual ABC. Thus, the problem turns into counting the total number of strictly increasing subsequences. Okay, so pre equal to, I don't know, so A is 97, right? So we do 0. And we just say for oh no, that's right, pre is not. Pre shall be a big word because we want to restart, right? So for num of increase is 0. For word in word, if this is larger than pre, right, then pre equal to this. Else num increase plus equal 1, and if w is current is larger than this, then pre equal to this. If current is larger than pre equal to this, and current is not larger than Then we do this, and then we set pre equal to W. So pre always move on, right? So pre will equal to Z. That's not true. If the current W is not larger than pre, right, then pre shall equal to W as well, which means we can just say if this is smaller or equal to, then we do this, then we will return num this times 3 minus len would. Yep, that makes sense. Yep, that's that. Okay, minimize the total price of the trips. There exists an undirected and unrooted tree with n nodes indexed from 0 to n minus 1. You are given the integer n and a 2D integer array of length n minus 1, where edges indicate there is an edge between nodes AI and BI. Each node has an associated price. You are given integer array prices. Price, where price I is the price of the ith node. The price sum of a given path is the sum of the prices of all nodes lying on that path. Additionally, you are given a 2D integer array trips, where trips I indicates that you start the ith trip from node start I and travel to the node ni by any path you like. Now, before performing your first trip, you can choose some non-adjacent nodes. You can choose some non-adjacent nodes and have the prices. Return the minimum total price sum to perform all the given trips. So we need to find some non-adjacent nodes, any non-adjacent nodes, right? So it doesn't really matter. Then, shouldn't we do that as much as possible? Huh, I guess not necessarily. $50 nodes, 100 trips, price not larger than, and price I is an even integer. Okay, that's fine. So we have this first graph, and I mean, if we can have as many trees as possible, as many more nodes as possible, that might already be a good idea. I feel this might be topological sort. If you think about it, topological sort goes from the outside in. The ones only have one connections, and the ones from one connections on the outside, they must not be connecting to each other unless we have a case like this, right? Now, because it's a tree, right? Because it's a tree, that means we're basically finding the leaf nodes first, and the leaf nodes are the most abundant. And if we're really thinking about trees, and we want to make the most abundant nodes shall be the ones with, yeah, if we have topological sort, we have some nodes on the outside, right? They connect in to some other nodes. And these nodes might be, you know, they might connect, they might not connect, and they might, you know, connect to some other nodes. I don't know, this is not a tree, man. This ain't not a tree. Right? So we can say, okay, I can remove, I can do this in the first move. Right, and after that, I'm gonna put these are adjacent. So these adjacent cannot be halved. I see the point. I see the problem in this. Because what if these are of low price? What if these are all 2s and these are like 100? Right? And I want the minimum total price. Right? I want a minimum total. So there are two problems. One is which nodes to choose. Well, shouldn't we choose to do the nodes that are the largest? Nah, maybe not exactly. I mean, we should probably take a look at the trip. We should do the ones that gets visited the most often, because if we have a node that have, let's say, 10 to the 9th, well, 1000 is the largest value, but I never use it, right? And I have this one have value 10, but I use it every single time. Even though this is larger, we should not reduce this. We shall reduce this because we don't really care about this. So we probably should take a look at the trips, right? 0 to 3, we can, you know, find. I mean, it doesn't really matter. We can just pick any route and DFS everything. And I want to know what nodes are encountered in every single path. So 0, we can pick some 0. So we can do from 0, right? I want to know what are the nodes from 0 to 3. So how do I know it quickly? What is 0 to 3? Now 0 to 3, I can say, okay, it's 0, 1, 3. Okay, that's 0 to 3. How do I know that? Well, I'm at node 0. I go to 1, right? So if I have all the paths from 1, then I know all the paths from 0. And since n is 50, I will be able to record everything, right? So I know everything from 1. And 1 goes to 3 and it goes to 2. So every node from 3 to 3, so this one will return just a 3, right? This one will return, so from 3, we can say from every single position 3, and it's the end, right? It goes to nothing. So we can say, what do we say? The nodes, right? Oof. How do we do this? Exactly. How do we do this? The path. We can do path. Okay. With path, we pass a path in it. So when we hit 3, right? When we hit 3, so from 0 to here we have 0, 1, and to here we have 0, 1, 3, right? So we have when we hit this and doesn't have any more children. Yeah, when we hit 3, we have a path of 0, 1, 3. So now what we do is we record 0, 3, 0, 1, 3, and 1, 3, because you're ending at 3. Okay, you're ending at 3. 1, 3 is going to be 1, 3, right? And then from 3, you can keep going to the next, right? And then for that one, we can just pick out everything, okay? And you're at 3. You try to go next, but nothing goes. So everything at 3, you can say 3, 3 will have just 3 by itself, right? And of course, the trips can be reversed. That's also another thing to keep in mind. Okay, so at 1, we had to have 0, 1. So we should have 0, 1, give us 0, 1, right? And of course, 1, 1, we should have 1. And at 0, we do 0, 0 is at 0. Okay, so now with this, we can record all the paths, all possible combinations of, 2s. That's fine. So basically, right? Basically, we have 0, 1, 2, 3, right? If I have 0, 1, 0, 2, 0, 3, 0, 0, 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, and 3, 3. So this is O(n) squared, right? This is O(n) squared, total number. And we can create a, dictionary, so we can have all that. And then we go through the trips, right? The trips. So now this one I know I do 0, 3. So the nodes I go through is 0, 1, 3, 2 to 1. It's actually 1, 2, and 2 to 3. 2 to 3. That's an interesting one. How do you do 2 to 3? Well, you do 2 to 3 because we don't have this one. We only do 1 to 2, 1 to 3. Damn it. Are you saying we just... Maybe it'll be easier just to go... Okay. N equals 50. Maybe we sort this based on the front. Okay. And then for each one, if we sort 2 to 1, we know, and then we can do 2 to 3. That's a thought. That is a thought. So we can handle them, in certain capacity. So why don't you redo this, right? So basically we can do this as the root, right? So we can do this. We have 0 start. Okay, we have 0 start. We will have 1 node. 2 start, we have 1 and 3, right? And maybe 3 stars anyway. And then we use this as a start, and we try to go to 3. And this is the start, right? And then we go, just DFS. We find this, we record what we need to do. And so there's actually going to be 2, 1 and 2, 1, 3. There's going to be 2, 1, 3. That's 2, 3. So these are the nodes we'll go through, right? And maybe we can have a counter of this. We have 2 encountered twice, right? 1 encountered 3 times, 3 encountered twice, and 0 encountered once. Okay, then what? Yeah, we can figure out how many times each node gets encountered. That's cool. right? That's cool. We can do that without having to repeat the whole thing. Then what? Then we check the score, right? We say the score is we can sort it. So if we sort it, we have 0 with 2, 1 with 2, 3 with 6, and 2 with 10, right? Then what? Then we need to choose which one to slash. How do we know which one to slash? Interesting. How do I know which one to slash? Which one to slash? And I mean, I can know which two are adjacent because of the edges. Yeah, I can know that. I can turn into a set. So I can say if I slash, hold on, how many do we have in total? We have 50, right? N is only 50. What are you saying? You want to brute force this? I mean, what I'm thinking, right, in this case, I can say that doesn't really matter. Well, I mean, it does matter, right? We can say we'll sort this. I don't really have to sort this. We just say, okay, I want to slash 2 by half. Okay. Okay, if we slash 2 by half, which is this, right, by half, and then we say, can we slash 1? Then we have to set up, like, let's say, a set of things that cannot be slashed because it has to be non-adjacent. So 2 is connected to 1, so 1 cannot be slashed. So this has to skip. And 3 can be slashed, so we slash 3, right? And then 0 can be slashed, so we just 1. And situation number 2 will be I do not slash 2, right? I do not slash 2. And then I can slash 1, and I cannot slash these. What are you saying? Like for each node, you can choose to slash or not slash, right? Okay, then you'll pass down. It's like backtracking. Yeah, I don't know. Backtracking? yeah, if the tree gets really complicated, a node is slashed, and then a bunch of other nodes cannot make any move. And a node is not slashed, the next node can slash or not slash. We're looking at 2 to the n, right? 2 to the n. What's 2 to the n? 2 to the n. Well, it's 2 to the 50. That's a ridiculously large value. I'm not sure, man. I'm not sure if that is the best way. And of course, trips might involve, right? Trips might involve every single node. So we might have to involve every single node. We might have to involve a single node. And the question is, yes, which ones we slash will give us the best chance? I don't think analysis will help, because you don't know the relationship between them. Right? You don't know. So you have to really try it first, because in this case, right, if 1 is really big, if 1 is 1000, right, then the minimum will be to slash 1, because you do other things, the amount of decrease is not enough. Then how do you know you need to slash 1, like slash this? You don't. You can say, okay, the total contribution from each, I can calculate the contribution, right? You can say, okay, the contribution I calculate is, let's say this one contribute 20, this one contribute 6, right? This one contributed 12, and this one contribute 2. So we have these value, right? Then you can say, because of these contributions, when you slash this, you get 10, right? You slashed 10. You go for the maximum, right? You go for the maximum value. But what you don't know is the relationship, right? You can slash the maximum, and then it can prevent you from slashing some of the others, right? Some of the others. I can totally make a situation where this will be the maximum, and you slash that, then you cannot slash all these 3, because they produce 5, right? This one produced 10 benefit, right? And the 0 produce 1 benefit if you slash. The 3 produce 6 benefit, right? 6. So altogether, if you slash these 3, it gives you 17 benefit. So all I need to do is to make this 1, make it bigger than 20. So make it like 10, right? Make 1 into, 12. It doesn't even have to be 12, because I have to go there 3 times. So I can because just the number 3, so 17, right? So I just need to be this one slashed in half, and the benefit is smaller than 17. So I can say 1 is, 7. No, I cannot do 7, 8. Okay? Let's say 1, the price is 8. If it's 8, then this one will come to 24, right? Then I say, I'll slash this. But when you slash this, you only have benefit of 12. Whereas as you slash others, you can give 17. So that's not it. So no, No, I mean, all this shows that you cannot pick and choose based on so-called analysis. I think what it comes to is indeed to find what are different ways to slash all the nodes that's involved. We have the nodes, right? We have the nodes, and then we know who are connected to whom, okay? And the nodes that are, yes, think about this way. We have these nodes that are involved, and the nodes that are not connected to anybody, they can be slashed no matter what, right? So those are not part of the concern. Okay, how do we know there's some nodes that's not connected to the others? We know that if that node does not, yes, it's the things it's connected to, yeah, it's adjacent, right? It's adjacent neighbors does not contain all these things. So what do you suggest? I mean, for each one, right, we can find its immediate adjacent and to see for everything if they're part of it. If it is, we include, right? If they're not, we don't include, right? And the next one, isn't that just like union find? But it cannot do union find. What we want to know is which ones cannot be slashed at the same time. That's what we want to find. Which ones cannot be slashed at the same time. So maybe it is. It is just, brute force. That seems so wrong, That seems so wrong. That just seems so wrong. Maybe the path can help us already to identify if there's anything that's not part of anything. Okay, so we're in the path. Okay, this is a one path. Oh yeah, the path can help us. We're in this path, right? So we already know 0 and 1, and then 1 and 3, they're all connected. So what do? We can say these cannot be off at the same time, right? So we know 0, 1, 1, 3, these cannot be off at the same time. And 1, 2, but basically it's 1, 2 cannot be off at the same time. And then this is 2, 1, and a 1, 3, so it's the same. We already have it. So from the path, we know that, which is needed for calculating the total. And we also know these are the pairs. Like they cannot be at the same time. So how do we use this? Which means we can say, if I want to slash 0, then I cannot slash 1, which means I can slash 3 and 2. But how do I do this better? I mean, the connections is already here. We're already here. We already know who's connected to whom. All the edges are already there, right? All the edges are already there, and then we already have 0 connected to 1, 1 connected to 0, 2, 3, right? 2 connected to 1, and 3 connected to 1 as well. Right? So I say if I shut down 0, no, if I do 0, right? I allow 0 to slash. Then we know 1 is shut down, like whatever here is shut down, which means whichever is connected to those can all be slashed, right? Like whatever is connected can all be slashed. So we go to those, and then we'll slash those. When you slash those, whatever they're connected, they cannot be slashed. Nope, I haven't formulated a good thought on this. I need to give this a little bit more thought. We'll save this for another day. All right, I'll see you guys tomorrow. Adios.